After studying this module, you will be able to understand about the mechanism of acid hydrolysis, mechanism of base hydrolysis, mechanism of base hydrolysis through SN2 type mechanism, mechanism of base hydrolysis through SN1CB mechanism, the role of conjugate base for finding rate of reaction, direct and indirect evidence in the favor of conjugate base mechanism. Rate of reaction gives misinterpretation for the mechanism of the hydrolysis reaction, but substitution reaction in aqueous solution is found to be accelerated in presence of acid or bases. The pH of solution is therefore deciding factor for nature of the product in the hydrolysis reaction and rate of the reaction. If water form a complex in case of acidic medium, then the attacking ligand would be H2O, while if the reaction is proceeded in the basic medium, that is in higher pH than 7, then the attacking ligand would be hydroxo group. Now let's learn about the acid hydrolysis reaction in case of octahedral complex. The reaction in which water molecule replaces a coordinated ligand from the complex species in an aqueous medium is termed as equation reaction or acid hydrolysis. The rate of hydrolysis reaction for the reaction of this type can be represented by an equation CONH3 5Cl2 when attacked by a water ligand. The product CONH3 5 H2O produces and Cl minus leaving group moves out. This reaction has been studied and it was found to be first order in the complex, that is minus d by dt into concentration of CONH3 5 Cl2 is equal to Ka into concentration of CONH3 5 Cl. Here rate constant Ka represent reaction in acidic medium. The rate of reaction would be dependent only on the concentration of the complex. That is, in this case, water doesn't affect the rate of reaction. However, the rate law alone does not indicate whether these reactions proceed by SN1 dissociative reaction or SN2 associative mechanism, because even if water comes in the mechanism, that is, even if reaction is of SN2 type, the rate would depend on substrate and concentration of water. But because of very high concentration of water, the change in concentration of water cannot be predicted. So, the rate of reaction would depend on the rate of substrate only. Means finally you will be able to see the substrate whose concentration is affecting the rate of reaction. We can have different tools by which we can find out whether reaction is proceeding through SN1 or SN2 reaction. Let's learn about the factors that affect the SN1 or SN2 type mechanism, and on the basis of that only we can conclude whether the reaction is proceeding through SN1 or SN2 type mechanism. Let's learn about the first factor, which is charge on the metal complex. An increase in the positive charge on the metal complex species decreases the rate of acid hydrolysis. Then we can predict that because of the increase of the positive charge on the complex species, the bond between metal and leaving group becomes stronger. That is, the dissociation of metal and leaving group would be difficult. So this kind of reaction cannot undergo through the dissociative mechanism, and before degrading metal species with leaving group, attacking ligand can attack over it. So it is preferred that the mechanism would undergo through the SN2 or associative mechanism. An example of acid hydrolysis reaction is shown here in the scheme, in which water replaces Cl ion to produce CONH3 whole 4 ClH2O, which when further replaced by water in a slow process to produce CONH3 whole 4 H2O whole 2 3 plus and Cl minus replaces. The increase in charge on the complex would make the breaking of MCl bond more difficult. You have seen in the example, in the first case, when the overall charge on the metal complex species was +1, then removal of Cl minus was easier and reaction was fast. But in second step, when overall charge on the metal complex species was +2, in that case removal of Cl group or removal of leaving group was difficult by water molecule, and therefore reaction becomes slower. So this reaction, if we see this reaction, what we obtain that the rate is dependent on the charge of the complex species. Higher the charge on the complex species, slower the rate. So this shows the reaction is following SN1 type mechanism, because if reaction would have been SN2 type, then with increase of charge, rate of reaction should increase. The increase on the charge on the metal complex would make the breaking of MCl bond more difficult, hence the rate of reaction is decreased here. However, if it takes place through SN2 mechanism, the rate of reaction should practically unchanged with any change in the charge of the substrate. Now, the second factor that can affect is the effect of chelation. An increase in the steric crowding around the metal ion preferably favors dissociative nucleophilic substitution reaction, that is SN1 mechanism. For example, when we consider CONH3 whole 5 Cl2 plus complex and NH3 molecule is replaced by ethylene diamine for the determination of rate of acid hydrolysis reaction, then what we obtain in case of CONH3 whole 5 Cl2 plus that have shown in the scheme, when Cl is replaced by water, the reaction was fast. But if it is replaced in the second example, in case of COEN whole 2 NH3 Cl, when Cl is replaced by water, then the product COEN2 NH3 H2O forms, but in this case the rate is slow. So it has been observed that the chelation shortens the CON bond distance, that transfers more electron density towards the metal ion. This should enhance the rate of acid hydrolysis. However, according to the solvation theory, the relative rates of acid hydrolysis of chelated complex decreases because of hydration of any species decreases its energy and thus stabilizes it. The higher the charge and smaller size of the complex species results higher extent of hydration, subsequently it stabilizes. For example, in case of CONH3 whole 5 Cl2 plus, which was hydrated, Cl minus decomposed to form CONH3 whole 5 3 plus, again it is hydrated, and then if water is added to it, the product that used to form is CONH3 whole 5 H2O 3 plus. While we have another reaction in which COEN whole 2 NH3 Cl 2 plus hydrated, when decomposed it forms CONH3 En whole 2 3 plus, and when water is added to it, the product is COEN whole 2 NH3 H2O 3 plus. The intermediate COEN2 NH3 3 plus of the chelated complex is bigger in size than the intermediate CONH3 whole 5 of non-chelated complex. Hence, the rate determining step of chelated complex would be slower than that of the non-chelated complex. It is evident that the chelation factor can be explained with the help of dissociative SN1 mechanism therefore, because with crowding rate of reaction is increasing, and since crowding affects the rate of reaction, so breaking of metal Cl bond is easier. Now let us move towards the third factor that we call effect of leaving group. The rate of acid hydrolysis of CuNH3 whole 5 Cl2 plus complex during the replacement of Cl with water molecule depends on the nature of leaving group, because rate determining step would be the bond breaking step. It has been observed that the reactivity of leaving group decreases in the order bicarbonate is having higher reactivity than nitrate, which is having higher reactivity than iodide, which follows Br minus Cl minus sulfate, fluoride ion, acetate ion, thiocyanate ion, nitro ion. Since the strength of the ML bond is directly proportional to the basicity of the leaving group, the rate of acid hydrolysis decreases with the increase of the strength of MX bond. That is, with the increase of basicity of the leaving group, the rate increases. This indicates that the rate determining step for the acid hydrolysis involve the dissociative mechanism, that is SN1 mechanism. We can summarize these factors like charge of complex if increases, rate of SN1 reaction will decrease. Basicity of leaving group if increases, then rate of SN1 reaction should decrease. With increase of solvation, rate of SN1 reaction should increase, and with the chelation or increase in the steric factor, the rate of SN1 reaction should decrease. Now we can jump towards a different type of reaction which is nearby this acid hydrolysis. This is called reaction without metal-ligand bond cleavage. The substitution reaction takes place without metal-ligand bond cleavage is the reaction where metal-ligand bond preserved after the reaction. For example, in case of CONH3 whole 5 OCO2 plus H plus ion added over it, then the product that used to be formed is NH3 whole 5 COOH2 3 plus CO2. During the conversion of carbonate amine cobalt third complex into the aqua complex, the OO bond breaking takes place, rather COO bond. This observation has been experimentally verified by labeling oxygen by its O18 isotope. NH3 whole 5 CO O CO2 plus 2H3O plus, where O oxygen is labeled by its 18 isotopes, O18 isotopes. Then the product that used to form is NH3 whole 5 CO O OH2 3 plus CO2 plus 2H2O 18. Here what you find, oxygen which was in the medium which was labeled by O18 didn't come with the substrate NH3 whole 5 CO O CO2, but it removes after the reaction. So in the mechanism that I have shown in the scheme, H plus ion attacks over oxygen part of the carbonate group and it forms NH3 5 CO O COH C double bond O. So this reaction is fast enough, and now the reaction undergo a rearrangement, and now H group is attacked over the oxygen part of the carbonate group, and after this the molecule slowly decomposes and removes CO2 group, by which the product NH3 whole 5 COOH forms. Now after getting H plus from the surrounding, it forms NH3 whole 5 COOH2 3 plus. The mechanism proves that these types of reaction are decarboxylation reaction. The chloro complex CONH3 whole 5 Cl2 plus has been converted into its nitro complex after reacting with NO2 minus. The reaction doesn't involve cleavage of metal-ligand bond because of the formation of aqua complex. That has been shown in the reaction scheme given here. CONH3 whole 5 Cl2 plus NO2 minus will produce CONH3 whole 5 NO2 2 plus Cl minus, but this is not the example of simple substitution type reaction. It is the reaction in which metal ligand cleavage has not taken place, but in between cobalt OH2 molecule has formed, and this intermediate have used to form another complex CuNH3 whole 5 NO2 2+. Now let's learn about the base hydrolysis of octahedral complex. Hydrolysis of octahedral complex in presence of hydroxyl group, that is at higher pH, then is known as base hydrolysis. It is observed that rate of hydrolysis of complex in basic medium is faster as compared to the acidic medium. Base hydrolysis is an overall second order reaction, being first order with respect to complex ion and with respect to hydroxyl ion. The rate is therefore represented as R equal to K into concentration of substrate into concentration of OH minus. Amine complex of cobalt third has been studied very well with respect to the base hydrolysis. For example, when CuNH3 whole 5 Cl2 plus OH minus reacts, the product that used to form is CuNH3 whole 5 OH2 plus Cl minus. This can be proceeded by any of the two mechanism. The SN2 mechanism we are putting here. CuNH3 whole 5 Cl2 plus, when attacked by OH minus will associate with the complex to form 7 coordinated intermediate, that would be CuNH3 whole 5 Cl OH plus, and in the first step of the second step Cl minus will be removed and the product CuNH3 whole 5 OH2 plus will be produced. According to rate of hydrolysis, it can be represented as R should be equal to K into concentration of substrate into concentration of OH minus. It has been observed that the above mechanism fails to explain some of the experimental evidences. At higher concentration of hydroxyl ion, reaction rate becomes almost independent of hydroxyl ion and seems to be first order with respect to substrate only. This can't be explained by assuming SN2 mechanism. So we can predict whether reaction can undergo through SN1 mechanism or it can have some other mechanism. In case of SN2 mechanism, the rate of base hydrolysis directly depends on the strength of nucleophilicity of attacking ligand. The concentration of NCS minus, NO2 minus, azide ion do not affect the rate of hydrolysis of amine complex, even though it has been observed that these are equally strong nucleophile like OH minus ion. It is also evident that the rate of hydrolysis of amine complex is dependent only on the concentration of complex ion. The SN2 mechanism is therefore unable to explain the cause of effect of rate of base hydrolysis alone by OH minus, and no other strong nucleophile should influence. So we must have to have another mechanism for the reaction. Scientists observed the reaction and then proposed another mechanism called SN1CB mechanism, that is conjugate base type mechanism, in which the complex CuNH3 whole 5 Cl2 plus acts as Bronsted acid, which was converted into its conjugate base CuNH3 whole 4 NH2 Cl plus. The conjugate base is obtained by removal of a proton of amine group coordinated with the complex. Conjugate base is an amido complex since it contains amido group NH2 minus. OH minus ion acts as a base and is converted into its conjugate acid H2O. So you can see the reaction would be CuNH3 whole 5 Cl2 plus OH minus. In the first step, convert CuNH3 whole 4 NH2 Cl plus water. The equilibrium constant for such reaction would be concentration of CuNH3 whole 4 NH2 Cl plus into concentration of water divided by concentration of CuNH3 whole 5 Cl2 plus into concentration of OH minus. It has been observed that the conjugate base CuNH3 whole 4 NH2 Cl plus is more labile than the complex CuNH3 whole 5 Cl2 plus. Hence, it undergoes SN1 dissociation mechanism by a slow step to lose Cl minus ion and form a 5 coordinated intermediate species. the 5 coordinated intermediate species, after reaction with water, it forms a final product of hydration, and the reaction is CuNH3 whole 4 NH2 2 plus. When react with water, it produces CONH3 whole 5 OH 2 plus. Now let's go to learn about the direct and indirect evidences in favor of conjugate base mechanism. The conjugate base mechanism have been experimentally verified, and following evidences were given in favor of it. It has been observed that second order kinetics can follow SN1CB mechanism because of equilibrium constant of the reaction. It is obtained very fast, and conjugate base present at equilibrium, that is K is small, since the reaction second involves dissociation of Cl minus from the conjugate base. It is slower than first and third, thus the rate determining step is R equal to K into CuNH3 whole 4 NH2 Cl plus. From reaction 1, K should be equal to CuNH3 whole 4 NH2 Cl plus divided by concentration of CuNH3 whole 5 Cl plus into concentration of OH minus. So CuNH3 whole 4 NH2 Cl plus should be equal to K into CO into concentration of CO into NH3 whole 5 Cl2 plus into concentration of OH minus, and therefore rate should be equal to K into concentration of CuNH3 whole 5 Cl2 plus into concentration of OH minus. As a result, R should be equal to K dash into CuNH3 whole 5 into Cl plus into OH minus. The second evidence that was given in favor of SN1CB mechanism was at very high concentration of OH minus ion, the rate of base hydrolysis tend to almost independent of OH minus. This observation can be explained by SN1CB mechanism only. If the amount of OH minus ion added is very large, there would be very little difference in the concentration of OH minus produced after adding. OH minus can be taken as constant so that the rate of hydrolysis can be given by the formula R equal to K dash into concentration of CuNH3 whole 5 Cl2 plus into a constant. The third evidence that has been given in favor of the SN1CB mechanism is the ligand like NO2 minus, NCS minus, N3 minus etc. are strong nucleophile than OH minus, but they do not influence the rate of hydrolysis of amine complex. This is explained as strong nucleophiles such as NO2 minus, NCS minus, N3 minus are not as strong base as OH minus. Hence they are unable to extract a proton from the amine of the complex to yield conjugate base of the complex by reaction first. So hydrolysis cannot proceed through SN1CB mechanism by these ligands. The fourth evidence that has been given in favor of SN1CB is it has been also observed that for the proceeding of reaction through SN2 mechanism path, OH2 minus is a better nucleophile than OH minus. The OH2 minus can be generated by the action of H2O2 on OH minus. So when OH minus attacked on H2O2, H2O and OH2 minus will generate. Therefore, it is assumed that the rate of base hydrolysis increases the addition of H2O2 on SN2 mechanism because H2O2 converts into HO2 minus as a beta nucleophile. However, it is noted down that the rate of base hydrolysis decreases with addition of H2O2 because the concentration of OH minus decreases, which is necessary for the production of conjugate base. Experimentally, it has been observed that addition of H2O2 actually decreases the rate of base hydrolysis of amine complex, which therefore strongly favors for the SN1CB mechanism. The fifth evidence that has been given in the favor of SN1CB was the isotopic exchange studies on base hydrolysis using 18OH supports SN1CB mechanism for base hydrolysis of cobalt 3rd amine complex. It has been evident from the above explanation that the rate of base hydrolysis is million-fold faster than acid hydrolysis. The reason for faster rate of base hydrolysis over acid hydrolysis is proton abstraction from the coordinated ammonia in the reacting complex, which forms a conjugate base, that is CONH3 whole 4 NH2 Cl+, which act as the driving force the dissociation of Cl- because by formation of NH2-, electron density on the metal complex substrate have increased, which increases overall negative environment around the cobalt, and because of that steric reason CO-Cl bond breaks from the product. Now let's summarize the overall findings. Kinetic study of hydrolysis reaction gives misinterpretation about the mechanism of the reaction. The rate constant for hydrolysis of CONH3 whole 5 Cl2+ in basic solution is million times faster than that obtained in acidic solution. If charge on complex or basicity of leaving group or chelation increases, rate of acid hydrolysis decreases. However, with increase of solvation, rate of reaction of acid hydrolysis increases. The reaction without metal-ligand bond cleavage are a type of decarboxylation reaction. The base hydrolysis of complexes follows million times faster than the acid hydrolysis. Due to dependency of base hydrolysis on OH- ion, the mechanism follows SN1CB pathway. The ligand NO2-, NCS-, N3- have better nucleophilic character but are poor base, hence unable to abstract proton from the complex, hence are unable to enhance the rate of hydrolysis.